I'd like to, first of all, thank the organizers for inviting me to talk at this very select meeting. I should say that the title is overwhelmingly appropriate for what I'm going to talk. For me, it's tremendously complicated. That means complex. And I'm going to really present results that were not available a week ago. In fact, even the transparencies I'm talking about were not ready until 2 hours ago. That's the Brazilian way. But this is, in fact, work of collaboration between the University of Delft, Technical University of Delft, and ourselves, and a number of people in Brazil. So I'm going to talk about geochemical modeling of water flood of oil reservoirs with CO2 solved by the wave curve method. The only thing I know something about is the last part. I hope the audience can manage the first part. Where do I point? This is not it. Okay. In summary, the challenge is to incorporate geochemistry when you inject water to displace oil. The point is that usually one injects water to displace oil in reservoirs. And the water that's there already has a reasonably high salinity. On the other hand, the water that you have available in order to inject further water could very well have a different salinity. And that's something to be discussed. Another issue is that we'll have an unusual situation of calcite reservoirs that are really oil wet. And I guess the reason is that oil has been there for quite a while. And another issue, which is, I guess, determining the whole thing, is that we have a large amount of carbon dioxide in the reservoir. So producing oil from that reservoir will release lots of carbon dioxide, which is exactly what we don't want to do. Can we inject it back so it doesn't go to the atmosphere? These are some side issues. So I guess that's what I wanted to say. Now, about 20 years ago, a number of researchers, including Norman Morrow, found that water composition can affect oil recovery by something like 10%. 10% of a big number is enormous. So what he noticed is that potentially when you inject salinity, water with salinity that's rather high, it's like seawater, the recovery curve is like this is in time. If you, after a certain time, you modify the salinity, say you put lower salinity, the recovery is more. So that's what he observed, and it has been, there's been a number of papers on it. For instance, this. The explanation is not complete, and that's one of the difficulties we have, is that the geochemical literature and the petroleum literature is not complete on this. And so let me talk about what's the application. Of course, here in Brazil, we talk about the pre-salt. There is a high quality oil. And this salt layer makes it not extremely different from the oil being in the moon. There are all sorts of technological challenges. So exploring this oil is expensive. So you have to make sure you get as much as possible. Otherwise, you might as well leave the oil there. Okay, this doesn't work, but this does. Okay. Given these results of Morrow, it seems natural that you want to put the geochemistry in multi-phase flow simulators. So one issue is that the data there is in geochemistry is not available in a format that's user-friendly. The best we have is in software. So one very important idea our collaborator had is to use this software to create lookup tables for essentially all the important coefficients that enter the evolution equation, the equation that govern the flow of oil. So I guess this was an extremely important idea in practice. That's first item about geochemistry. Another issue is that carbon dioxide. Carbon dioxide affects a lot properties of oil. And how much oil dissolves, how much carbon dioxide can dissolve in oil depends on the oil pH and other salt component. Therefore, we have to also take into account the transport of these chemical compounds and ions. Once you speak of ions, you remember that actually there are surface charges on the oil as well as on the calcite. And these charges affect properties of that are important for oil flow, such permeability. So that has to be taken into account. Exactly how? That's really, if you look for papers about this issue, you don't find them, except for rather academic ones. They say, you know what happens at low value, you know what happens at high value. What do you do in the middle? Interpolate. There are two possibilities. Either it's not known or they are stored in some bin in some company and without being published. So from the point of view of people at Delft who understand petroleum reservoirs, a major challenge was to understand geochemistry. And they found out that using software was very easy. This software FreeQC that describes geochemical properties of in the solution is from the Geological Survey Service in the United States, so it's free. And it's a treasure of information. Okay, so I should say that's the main challenge for them. The main challenge for me was to try to understand what they were saying. So when you have water and oil flowing in reservoirs, you can schematically represent it by a diagram like this. And there are a number of components, chemical components in the water, and a few, like the oil, like carbon dioxide, ionized carbon dioxide, etc., 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 etc. There are a number of these. Which is more important? That's a problem. I guess before determining which is more important is how many do you want to have. So we assume that reactions occur in the water fast enough so there's local thermodynamic equilibrium. So the number of degrees of freedom can be obtained by Gibbs phase rule. I thought that this was magic. And it isn't. It turns out that we end up only with 2 degrees of freedom besides temperature and pressure, which are kept fixed. So we have all those chemical reactions there, but if you assume that there are in equilibrium, there are only 2 independent variables for our choice, and we chose these ones. And I'm going to come back to this point. And having chosen these ones, we can find how the concentration of one of those compounds, calcium ion, in the water depends on those 2. So it's a plot like this. So this is done for a number of such compounds. We found it. I don't know. This for me is a function of chloride and hydrogen. For my collaborator is a table lookup. And I learned that the 2 things mean the same. I don't see where the table is. Well, one cannot eat on such a surface as this, can one? So call it a table is very peculiar. Another important issue is surface complexes, which I guess I'm not going to talk about them much for the very simple reason that in the first results we are not taking them into account. But they have to be taken into account. That's the way chemistry interacts with physics. So that there are also charge densities which they actually shield these charges, and they are important. And it turns out that we create what's called table lookups, and this is another result for a number of compounds, the concentration of a number of compounds in terms of just 2. pH and sodium chloride concentration. This is one concentration, there's another concentration. So you see all these concentrations of several compounds that have the list here change reasonably with sodium chloride density. So sodium chloride is crucial, and that perhaps explains why low salinity water injection is so relevant. I should say that I'm parroting. Okay, please.
So is it because of sodium chloride, or is it because of ionic strength?
I think that the little I understand that sodium chloride sort of blocks some of the ionic strength, and perhaps I'm saying something silly. We don't know yet, really, which is which. We have not. The 2 are not entirely independent. Therefore, the honest answer is that I don't know, and probably we don't know. This is a very important point. Thank you. So again, on surface charges, and that's to point out that that's a mechanism, and some details on surface charge, which I'm going to skip. More on mechanism that I only vaguely understand. No, I should say that I don't understand them at all, but perhaps some in the audience understand them. And the reason why I'm showing this is to justify why this is a complex situation, but there will be a surprise. So what's the effect of all this on relative permeabilities? So relative permeabilities, they basically translate pressure gradients into flow. And depending on their shape, they will be more or less water displaced. I'm sorry, who cares about the water? I wonder, how is it that petroleum reservoirs people, they always use water saturation as a variable when they really care about oil? I had to find that. Perhaps in the future it will be otherwise, right? So I guess all these transparencies are to justify that through the mechanism of oil or water wetness, how the charges and complexes affect the relative permeabilities, and that affects the recovery. And this is qualitative. Therefore, it's just a reminder. Who's a petroleum engineer here? I guess you are? Or a hydrologist? Or both?
I can admit to knowing a little bit about petroleum.
Good. So you know more than me about this. For me, I want to know how these curves depend on which variables. And why, it's beyond me. Okay. And then the chemistry, a little more. You could assume that chemistry has to do with conservation of atoms. That was I naively thought, but no. It's you group these atoms into ions that keep unchanged. So this way you reduce the number of variables in your system. And that's something I always welcome. So that's the concept of master species, which I guess there are half a dozen or so. We originally had 15 or 16 species. Now we have only 6 or 7, including oil. Notice that oil in the petroleum is different from, say, oil in the carbon dioxide. They're different. So we have these are the species that are conserved. Now, equilibrium relations. It turns out that pairs of compounds can react to form other pairs of compounds, but they don't go all the way. It can go back, and they form an equilibrium, and you can compute how much you have of each depending on certain equilibrium constants, which are these Kas, and they are defined in terms of activities of each of these. So as far as I'm concerned, these are relationship between left and right concentration, or activities, really. And so if you assume that you have chemical equilibrium, that means that you really can express some of these quantities in terms of others. So they represent constraints in the system, or evolutionary system that I have to solve. That's in mathematical language. In more down-to-earth language, this means I can, if I'm lucky, I can obtain some of the variables in terms of the others using these expressions. So using these expressions and the data on observed equilibria in different proportions, you can find regression expressions or lookup tables. I keep forgetting this. There's something else. If you want to be serious about your charge activity, you have to take into account the biovehicle theory that relates ion concentrations to those activity coefficients that go there in the previous page. And this is one of the coupling that's global. All the species are connected through this. Another constraint. So that's why I thought that we had to find out what's the math of systems with constraints, evolution system with constraints. So these are details of the usage of the previous concept. Again, there are other things that are not exactly chemical, they're perhaps physical chemistry. That's the concentration in the decane of CO2, I believe, depending on pressure, or perhaps it's the opposite. I should say I don't know. This is the density of oil in terms of pressure. Pressure will be kept constant, but rather high, because we are at 10,000 kilometers, 10 kilometers. So now we're going slightly to more familiar ground, that's as far as I'm concerned, but not quite. So this is the number of hypotheses that we make on the physical model. So we have high pressure, limestone, rock. That's interesting because limestone means carbon dioxide. That means there's also a reaction between the rock and the fluid. I should say that this is much too complicated. For me, this has nothing to do with mathematical model. If there are no equation, where's the math? So that's the pardon?
The physics problem.
That's the physics, and this betrays it. So initially we considered these 7 species, but even that is too much. Or no, that's right. That's 7 species. That's what we end dealing with. We throw away all the others. Why do we do that? We can either do something that we can perhaps solve, or we can try to solve reality and not solve it. So we prefer to solve something if it's not reality. So of all the other relationships, remember we had a page of equilibrium reactions. We chose these 3. And we repeated conceptually the whole procedure with only this. And the equilibrium of carbon dioxide in the oleic and aqueous phase, I think this is some relationship that, as usually, it has some exponential with some negative. I forgot what's the name. One of those laws. Sorry to. That's an important law, and I used to know it. Again, we count degrees of freedom, and this is a simpler problem. We only have one chemical species concentration as a variables, and we take this as hydrogen. So we have hydrogen, oil, and water partitioning, so that's a saturation. And we also have flow. How much oil is moving, or water, or fluid. So we have 3 independent variables, and all the densities, or I shouldn't call them densities, concentration, molecular concentration of each elementary master species appears here. So that's a concentration. Yes, a concentration, saturation of water. That's inside the water. That's CO2, for instance. And that's CO2 in oil. Then the fluxes of the same. And whoever is familiar with the fractional flow formulation of flow in porous media understands this. We have another one for hydrogen. And total oxygen. And there is some technical detail that I'll skip. It's better to use a combination of two of these rather than each of them. So in the end, we have 3 unknown variables and 3 balance equations. Okay? That's what we summarize here. 3 unknown variables, SW, concentration of hydrogen ion and flow, and 3 balance equations. Theory says the systems of 3 equations with 3 unknowns should have 3 characteristic speeds. Well, this is a peculiar system of conservation laws, and we mathematicians like to be compact. Since we don't understand the details, we might as well be compact. It's peculiar, but this one only has 2 speeds. And they are essentially the speed of propagation of chemical compound and the speed of the Buckley-Leavitt saturation speed. And there is the speed of propagation of pressure waves, which doesn't appear, which is infinite, and it has to do with this variable. So the infinite doesn't count. So we only have 2. So this is if we want to do calculations, and I'll spare you pages and pages of calculations. That's a part that I understand. And should say that this is rather recent. So this is a calculation of characteristic speeds. One of them has this form. That's the propagation of chemicals. And if this delta were 0, this would be propagation of ideal propagation of something in the water. But without this, with this delta, it's not exactly the same. And that means that propagation, the wave that propagates chemicals is not a normal contact wave. I don't know how you call it. Not a linear wave. So diffusion has, if it were a linear wave, diffusion would completely kill it. But molecular diffusion is small. So this is a relationship between left and right states in a shock. So we plot this in state space. That's the part that we like, and I'll show you results. I'm going to not to torture you with how you would do it. So I guess here we show a result of this calculation by putting together characteristic speeds and characteristic vectors and seeing solution path, which you have to be careful about. There are usually no shocks in chemicals, at least in water. So there's a trick here. So here is the state that you inject. The state, you see there's a hydrogen concentration which is rather high in this system of unit. And this is the state that represents the initial situation in the reservoir, not much hydrogen. And this is saturation. Whatever is not water is oil. So, following this, we construct a curve that follows from those equations, and this is the hydrogen wave.
We inject water with oil?
J-I-I-J. Let me see. Let me see. Well, let me see the simulation, okay? Actually, I should say that this is a calculation to verify a simulation. So let me show the simulation. That's not a bad idea if you recover more oil than you... let me see. Yes, exactly. We inject water with oil. Why is that? Simulator doesn't behave properly if you inject pure water. Okay? So the purpose here is to verify that we understand what happens. And that perhaps is easier for many people to understand it here. These are simulations for very different times here. So this is the profile of a certain time, the distribution of oil. So initially there is, all of this is oil, all of this is oil, and this is water. So there is a shock displacing the oil. There's a smooth wave behind. There's something that you don't see, but it's, the theory says it's a constant state. So there's a constant state in behind. And then there is a hydrogen wave, which is a chemical wave, which is this one. That's the simulation. That's what it does. And it does displace oil. And we are not injecting pure water here. Okay, but that has to do with the simulator. Our point is that the simulator provides this figure, and our calculation provides this other one. So this is, the green one is our theoretical calculation. You see the saturation looks very much the same, except that the speed of this other wave is rather different from, this one is rather different from the simulated one. Which do we trust? We compared this with the fractional flow theory. That's something they can find by hand with Buckley-Leavitt, essentially. And this one is less accurate than that. Therefore, we trust this more. And you see what happens? There's more water here than here. This means that more oil is displaced. So if you want to predict how much oil is going to be displaced, this will give you a pessimistic scenario. This is what should be observed. Why is that? I'm actually skipping details, as I have all the time. Why is that? Well, let me show you another simulation, this simulation. So this is a set of curves of saturation waves here for different times, and here is the calculation based on the wave curve method. You see that you don't see this, this green part is invisible here. Why is that? Simulation. It has numerical diffusion, it cannot do it. It's good that it was able to predict this hydrogen wave. Our amplitude of the hydrogen wave is much higher. So I should say that that was something that made me feel very good. So conclusions. First of all, geochemistry can be accounted for with some effort. Carbon dioxide, of course, is important. That was known, but now it's quantified better than before. And the wave curve method finds solution where simulators are inaccurate. I guess that's conclusions, and sorry for being too skimpy on explanations.